Hi, I am Satyam Agrawala and this is my presentation for final project. I have implemented a compiler which is a subset of c89. The compilation stages in my compiler are lexical analysis followed by parsing, followed by generating symbol table, followed by type checking. After this, if there are any errors, the compiler exits. If not, it generates an intermediate representation followed by two stages of optimization and then followed by MIPS code generation. The output files of the compiler is a pretty-printed source file, a symbol table, intermediate representation unoptimized and optimized depending on input of user, and then the MIPS code. In the stage 1 of optimization, I do peephole optimizations in the listed order. That is load address followed by constant expression optimization, followed by identity, followed by immediate instruction optimization, followed by strength reduction, followed by dead code elimination. In stage 2, I conduct a liveness analysis for which I create basic blocks and a block graph with entry and exit points. To calculate live temporaries, I initialize all the registers as dead, and then I get the exit blocks from the block graph. I add these blocks to a queue and iterate through this queue in a while loop. That is, if the queue is not empty, I keep on iterating. I get the top block in the queue and compute the liveness of that block. For every block, I backtrace through the instructions of the block. In each instruction, I store a list of an array. I store an array of registers with the liveness status of each of those registers. So if the computed liveness has changed from before, then I add the entry points of that block to the queue. If not, I just continue. Next, I do graph coloring. For this, I build the register interference graph. This is basically an n by n matrix. N is the number of registers. I iterate through all the instructions, and if at any instruction, whenever a register is defined at an instruction, I get the live registers from the next instruction and set a two-way edge between all those live registers and the defined register. After this, I remove nodes one by one from the graph based on the minimum number of edges and push them to a stack. If I'm able to remove all the nodes, then I'm good. But if at any stage I find that all the remaining nodes in the graph have more than 18 edges, which is the number of MIPS registers I have, then I emit an error for spill. Once done, I pop every element from the stack and assign MIPS registers to it. Based on this, I'm able to load and store only those temp registers which are live during a function call. Apart from this, I'm only storing and loading those S registers which are used in a function, and I'm also supporting more than 4 arguments in a function call. Now I'll give you a demo. So now I'm going to show a simple program which basically defines a matrix of size 4 by 4, and in a for loop from I equal to 0 to I equal to 4 to I less than 4, it will assign the value I to all the diagonal elements of the matrix, and in the end it will print the last diagonal element, and the value of that will be 3, which is what we should see when we run this program. Notice that here the branch condition has a constant sub-expression, the value of which is 4. And in this statement, which is essentially aii equal to I, this expression has a bunch of identity expressions. Now I'm going to run this program in 3 stages. One is the unoptimized stage, one is peephole optimization, and the other is with graph coloring. So the unoptimized stage gives a temp spill error. So I cannot generate MIPS code for it, but I can show how the other output files of the compiler looks like. So first is the symbol tables. It just shows all the variables in the global table, which has all the syscalls. Then this is the main symbol table. And then there is program.c, which is just a pretty print of the source file. And then there is ir.out. So this is the intermediate representation, and it has close to 60 instructions. First, notice that for this constant sub-expression, we have a whole bunch of const, mult, add, sub, less than sign instruction. Then notice for this long statement, which is essentially AII equal to I have close to 24 instructions. And this is the reason why we had a temp spell. Now I'm going to run it in the optimized with peephole optimizations. So this generates the instructions with peephole optimization, and notice it only has 33 compared to 60 previously. Notice in the branch condition, this has been folded into a single instruction which says less than sign immediate, and the value of the immediate has been calculated here as 4. So this has been done as part of constant expression optimization and immediate optimization. Also notice that in this statement, I am using load word of a variable directly. So this here I've optimized the load address, and similarly here. Also notice I'm using a left shift immediate here while calculating the array address for AII, the address for AII. Here basically I am replacing a mult instruction with a left shift immediate of 4, since my matrix is of size A44, and the second index of the matrix has a left shift immediate of 2. Also notice, yeah, so that's all. Now I'm going to show the MIPS instructions. So the MIPS instructions looks like this. There are 86 lines. Notice that this MIPS file uses registers from S0 till S7 till T4 to generate the instructions to run the code. Now I'm going to run it with the graph coloring. And this generates a set of instructions. This intermediate instructions are exactly same as the peephole instructions, but now they are showing the block to which they belong to and the temporaries which are live at each instruction. So the block graph can be seen here. So this code basically has 5 blocks, and these are the entry points and exit points. As expected, this file will have one block from the start of the main program, one block for the start label of the for instruction, one block for the end label of the for instruction, and one block for the return label of this main function. So that makes it, and one more block for the body. So that makes it a total of 5. And this is the register interference graph. This shows the assigned MIPS register for each node. Notice that this only requires 2 MIPS registers, and these are the edges. So I can show that in the MIPS file generated. In the MIPS file generated, first of all, there are only 54 MIPS instructions compared to 86. Here, first notice that I'm only storing 2 saved registers because those are the only registers which I used in my file. And also notice that whenever I make a function call, I'm not loading or storing any temporaries. Now I'm going to run this code on spin. The result of this is expected to be 3, and that's what we get. Now I'm going to show a little bit more complicated program just to prove that the register allocation is working correctly. So this is a file which generates, which calculates the determinant of an input matrix. Notice it has several large statements throughout the code. So I'll just run it quickly. So it's asking me for the size of the matrix and the values. So I'm going to enter a 3 by 3 matrix, and the result is as expected, -2. Now I'm going to show another file. This source file just shows that my compiler supports function with multiple arguments. So there are 2 functions here, one which takes 5 arguments and the other which takes 6 arguments. It is essentially going to calculate the sum of integers from 1 to 11, and print the result. And in this case, the value is going to be 66. So I'm just going to run this, compile and run this. And the result is 66. That's all. Thank you.